Okay, hello everyone, and welcome to the May 2025 LINCC Tech Talk. My name is Mi Dai, and our co-host is Colin Chandler. We are both LINCC Frameworks project scientists. I'm at University of Pittsburgh, and Colin is at University of Washington. LINCC Tech Talk includes presentations and demonstrations that showcase work done by the broader Rubin software and archive community with the goal of further enabling LSST science. Unlike traditional talks you might hear at a conference, Tech Talks highlights the technical aspects of the work being done. We hope this talk will provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in the analysis of LSST data. LINCC Tech Talk are delivered virtually every second Thursday of the month at 10 a.m. Pacific. Today we're joined by Amanda Wasserman, who will talk about her LINCC incubator program, RESSPECT. Amanda is a fourth-year PhD student at UIUC. She went to the University of Rochester for undergrad, where she worked on finding serendipitous supernova spectra in DESC data. She then came to UIUC, where she works on spectroscopic follow-up of interesting transient events. While in grad school, she has been a Center for Astrophysical Survey Fellow for 2 years, worked at Lawrence Berkeley National Lab for 3 months through the Science Graduate Student Research Program, and she was PI of the RESSPECT LINCC Incubator Program. For today's talk, please ask questions in Zoom or in the LINCC Tech Talk Slack channel. On Zoom, you can type your question in the chat or raise your hand. And as a friendly reminder, these talks will be recorded and will be posted on YouTube channel. With that, Amanda, please take it away.
Thanks so much, Mi. Yeah, like Mi said, I'm Amanda Wasserman. Today, I'm going to be talking to you about modular metrics for the LSST Spectroscopic Recommendation System. So just a really brief outline of what I'm going to talk about. I'm going to start with some motivation. So why do we need a spectroscopic recommendation to look through all the transients that LSST is going to see? And then I'm going to kind of have a past, present, and future outline where we're going to look at where was RESSPECT before the incubator, where did it start, sort of the present of what kind of upgrades did we do during the LINCC incubator, and looking into the future, what have we been doing since and what do we have planned going forward. So to start with the motivation of why we need a spectroscopic recommendation system, as I'm sure all of you probably know at this point, LSST is going to be a transient discovery machine. We're going to increase the discovery rate of transients by about 2 orders of magnitude. We're going to be seeing about 1,000 or so supernova every single night. And just because of that sheer magnitude of supernova and transients that we're going to find some really interesting stuff. We're going to find supernovae early. We're going to catch them when they're really young. And if we can follow up on them and get spectroscopy and more dense photometry as they evolve, we can learn a lot about their progenitor systems, and we can do things like better type 1a modeling, leading to potentially better constraints on our cosmology as parameter estimates. Another aspect that all of this data is going to allow us to do is find rare transients. I'm sure everyone's heard of, those needle in a haystack that we're really interested in, things like kilonova that we've only seen one of before. I think the estimates that if we can find them in the data, that there will be like 5 to 10 per year in the LSST data. And this is all fantastic, except for the main way that we go about classifying the types of supernova that we're finding, and the main way we learn more about the science and what goes into the supernova and the progenitor systems is through spectroscopy. And despite this huge increase in photometric data, our spectroscopic follow-up is going to remain about fixed. We'll only be following up on about less than 1% of all supernova that we find. So just a little bit more about the interesting work that we can do with these supernova. Things that the DESC is working on is identifying type 1As within the alert stream so that we can do a cosmology analysis to constrain things like W0 and WA. And then one of the main things I'm really interested in is determining what the contamination would be from other classes into this cosmology. So if we accidentally mistake a type 2 supernova as a type 1A, how is this going to impact what we find in our results? So yes, contamination is one of the leading causes of systematic error, and one of our goals is to minimize the contamination and maximize our purity. Some other interesting science that you can do with these transients are these unique objects. So on the top right, you have an example of a supernova 2022 PNF. This is some photometry that I believe is mostly ZTF. You can see that there's a poor salt fit to this. We don't really have a classification for what this object is. And most importantly, we don't have a way to go back and learn more about it now. We have a certain window of time that we can follow up spectroscopically and photometrically before these things start to fade. And once they're gone, they're gone. So this is just a really good example of something that maybe was really unique and interesting, but we missed it and we don't have the opportunity to go back and look at it. We want to make sure that that doesn't happen with interesting objects with LSST. And then on the bottom is an example of something that we did find young and was interesting and we followed up on. So this is 2020 OI. It's a type 1c supernova, and it was taken, the spectrum was taken during a rare early time bump in the photometry, so that you can see the spectra in purple there. And we can see that there's a composition model for the spectroscopy in black, and that it doesn't really fit what we see the actual spectra looking like. But if we consider that the supernova was maybe enriched by lighter elements, that the supernova exploded into some surrounding material, and we add this mass, we get a combined model that is this red line, and that follows much better our purple actual spectrum. And so we see the model much better fits the data once we figure out that it is exploding into this material. So yeah, from that we can find out about the supernova themselves, the elements in them, the materials they're exploding into, all sorts of interesting stuff like that. And so this is just the start of the examples of science that we can learn from these interesting objects. But it's really clear that with thousands of supernova a night that we're going to see with LSST, there's two things. We need a way to find these scientifically interesting objects, and we need a way to prioritize and coordinate spectroscopic follow-up to make sure that none of this stuff falls through the cracks, that we are finding everything interesting that we want to find. So this leads to this past that I was talking about. Where was RESSPECT when we started? What is RESSPECT? So RESSPECT is the recommendation system for spectroscopic follow-up. This is a machine learning algorithm that will recommend about 10 supernova per night to follow up on. So a much more manageable 10 supernova to look at rather than that 1,000 that we'll see every night. And if a recommendation system sounds familiar, that's probably because it does. Things like Netflix use recommendation systems all the time. They look at what you've watched in the past, what you enjoyed, what you didn't like, and based on that, it could recommend what it thinks is the best thing for you to watch next. Similarly, RESSPECT will look at what we observed before, how what we looked at was classified, and based on what we've seen, what we've learned, it will recommend the next best thing to observe. So what this looks like a little bit in the flowchart, we start with data coming from data management that turns into alerts. The alerts get sent to brokers, which get sent to the DESC TOM, or the Target Observation Manager. So that is compiles all of the broker inputs into one place where we can then query all that photometry. All the photometry and light curves get pulled into RESSPECT. RESSPECT uses a random forest classifier to classify things as type 1A or not type 1A. And somewhat unintuitively, it actually looks at these objects and says not what is most likely 1A, it says which ones am I least certain of, the things that it doesn't know if it's a type 1A or not. And from that, it recommends those least certain objects for follow-up, sends those objects to the TOM, and spectroscopic follow-up telescopes, so things like Foremost and Gemini, people who have time on those telescopes can query the TOM and say, okay, what are the interesting objects that we want to see tonight? They can then get a spectra, do a much better job classifying the object with spectroscopy. We'll have a then true label for what that object type is. It will get returned to the TOM, and the TOM will then send that back to RESSPECT. So RESSPECT will get these true labels from the spectroscopic telescopes, And then it takes the true label and the object it was uncertain of and puts that back into the training set. So the next time that RESSPECT sees another object that's maybe has a weird light curve or looks for some reason similar to that object that it wasn't uncertain of before, this time it's going to do a better job classifying and know exactly what it is. And so this is something called active learning, where each night we're going to add the objects with maximum new information to iteratively improve our training set. In this way, at the end of the 10 years, we're going to have a really representative training set of all types, like all the different variations within type 1a supernova, so that we can do the best job we can photometrically classifying all the million or so type 1as that we can use, so that we can use all of those photometrically classified objects in our cosmology analysis, not just the ones that were spectroscopically confirmed 1As. So just a little flow chart of what RESSPECT actually looks like. So we start with a baseline set that can be as few as 10 classified supernovas. So say 5 type 1A, 5 not 1As. This becomes our original 10-piece training set. We then can train our classifier based on this training set. We get an incoming pool set of data. So that's the things we observed for the night, the 1000 supernova that we just observed. The classifier will then classify these things, assign them a probability, and using our active learning strategy and additionally some information that we know about the telescopes and object properties. So for example, if an object is really dim, it might need way more time than a telescope has available. So it takes that into account. And from that list of how uncertain the objects are, prioritizing maximum uncertain objects, and considering telescope resources, we can produce a candidate list, which is just a ranked list of what RESSPECT thinks is going to be most beneficial to add to the training set going forward. A human can then come look at this list, choose that, of order 10 supernova that they have time spectroscopically to observe, query the objects, follow up spectroscopically, and append that true label to the training set, like I was saying before. And so you can see this is a whole loop that repeats every night. And like I said, it starts with about 10 objects in that baseline set, and it adds about 10 objects each night. And so this way we can build entirely our training set from scratch. Obviously, LSST is not online right now, so we are currently working with simulations. We're working with Elastic, which is a data set that contains about 5 million transient events. This is 25 different classes of objects, so we get to see all sorts of different light curves to work with. And most importantly, they have LSST-like alert structure. So we can analyze these objects as we will when LSST sends the real alerts. So we have the framework already set up when LSST comes online. We then have to do feature extraction once we have light curves before we can input them into our random forest classifier. We're not inputting full light curves, we're pulling features out of those light curves. So originally, there was a Bazin light curve fitting, and so you can see that on the top right, how you could fit this curve to the light curve and get out parameters that way. This was a bit time consuming, so I worked to implement instead the light curve package that Kostya Malinchev created, who I believe is here. And this is much, much faster, much more manageable on a timescales. And also you can see on the bottom right how our classifier improves as we add those 10 supernova each night. And you can see that actually this light curve package performs better than the original Bazin fit. We're also looking into potentially using a variational autoencoder going into the future, using information from the latent space of a VAE to use as inputs to our classifier. But this is just kind of already a really good example of why we need this modularity in RESSPECT. We want to be able to test different things, be able to just plug in, plug out, for example, different feature extractors. Once we have our recommendations from RESSPECT, we are also simulating what follow-up will look like. So this is some of the first realistic simulations of what LSST spectroscopic follow-up is going to look like. We are taking the recommended supernova and simulating them again, but with this time with their spectral energy distribution. However, SEDs are too perfect. We're not going to get spectra that look as good as the SEDs themselves. So we need to contaminate with the detector noise, seeing all sorts of things like that so that we get a more realistic idea of what we're going to be seeing. And for this, we've been working with the Foremost Tides team. So they're going to be performing spectroscopic follow-up of supernova with leftover fibers that they're not pointing at galaxies. And so we've been working with them to see what this might actually look like. So you can see on the right there, the original SED in orange and the noisy spectrum in blue. And we can look a little bit more of this with what spectroscopic follow-up is going to look like with Gemini. So on the left, you can see how these spectra are going to evolve with redshift. So obviously, as we get further away, the signal to noise is going down. And this just kind of gives us an idea of how well we're going to be able to classify the spectra and how far out actually in redshift we'll be able to identify what is a type 1a and what isn't a type 1a. And then on the right, you can also see some of our simulated data compared to real data. So here you can see the TDE and the kilonova are actually real, and the calcium-rich transient and 1A are simulated with our pipeline. So we can see that we're performing pretty decent simulation of what we're actually going to observe with these spectroscopic instruments. Once we have what our real spectra are going to look like, we need a way to classify them. Right now, we've been working with DASH. So DASH has you input the spectrum, and then it's going to do a couple things. It matches what it believes the best fit class is. So for example, this is a 1A. It estimates what the redshift is. And what I think is also really interesting is that it can take a known redshift or a redshift prior. So we can do things like work with the Photo Z team, work with Rail to get an estimate of what a redshift might be to do a better job classifying these different types of supernovae. And just some really, really preliminary results for what this pipeline is going to result in the end. This is just a look at our cosmology estimates with zero bias, and then so just straight type 1As on the left, and what it'll look like with contamination, a handful of type 2s, a handful of 1Bs, things like that, how that's going to be affected on the right. So it's clear that the pure sample of 1As is going to be beneficial in our analysis, and I will be finishing up that paper soon, so you'll be able to get a good look at the actual impacts of that very soon. So our thought with RESSPECT was, this is great. This is fantastic. It's working great for us. Let's share this with the community. Who else could possibly utilize this? What other science cases are there out there that might benefit from this? And so that kind of leads us to this present, or the upgrades that we made in this LINCC Incubator program. So our main goals for the LINCC Incubator was to make the spectroscopic recommendation system accessible to all. We want anyone who's interested in using RESSPECT to be able to. We want to pave the way for a modular approach so that folks with different science cases can come and just pluck out our type 1A classifier and plug in whatever they're interested in. And then we just wanted to make sure we have a lot of really good documentation so that kind of coming back to that accessibility, people are actually able to use the work that we completed during this project. So the first things first, we needed a way to make sure that the TOM that hosts all our data and RESSPECT can talk to each other. So some things that you can do from the RESSPECT side, you can ask the TOM to find hot transients, or say, get me the transients that have a new observation from last night. So you're just looking at the newest things. You can then do your own classification and ask the TOM, I want a spectrum of this. And then once that spectrum is reported with a label, you can query for the information about the spectrum, the classification to put back into the training set. Now, on the other side, from the follow-up side, if you have spectroscopic telescope time, if you have Gemini time, something like that, you can go and ask the TOM, hey, what spectra are wanted? What did RESSPECT say they wanted to look at tonight? You can then declare an intent to take the spectrum so that we don't have two different telescopes observing the same object in one night. We don't want to be wasting time when it's so precious. We want to make sure that we're utilizing this as best as possible. And then obviously report the spectrum and the label once you observe it. And the nice thing about this is that multiple recommendation systems can recommend. And so someone from the spectroscopic follow-up side could say, oh, I only want the 1As, non-1As, or someone else could say, oh, I only want anomalies. So we can sort based on that. And then also anyone can access these recommendations so that we're maximizing the amount of people that have, are taking this follow-up, and we just request that they report the labels once they find them. Some other work that we did was accessibility and storing of the RESSPECT data. So first things first, RESSPECT is now pip installable and has automatic releases to PyPy. Max did a fantastic job parallelizing the code, so everything's running a bit faster now, and also did some really good refactoring and cleaning up, so everything's neater and much more approachable. Michael also worked on creating a Docker container. Now RESSPECT is basically able to be deployed on any machine really easily. You just download, get the container and spin that up. So be it on NERSC or some other supercomputer you may be using, or even on your own computer machine. This is also having automatic testing on GitHub and has communication with an instance of the TOM. And the final thing that Max did, which was much appreciated, was that RESSPECT was storing all of its extracted features in just .csv files. And so we wanted a better way to access this database. And so Max went and created a MongoDB database for us to use. Great, so we have everything really set up to start working on this modularity. Now we need our first module that we're interested in, and for us, this was anomaly detection. So this is LACE, or the Light Curve Anomaly Identification and Similarity Search algorithm. This was done by Patrick Aleo, a previous grad student at UAUC. And so what LACE does is it actually analyzes light curves and uses a combined random forest algorithm and similarity search to identify anomalies. This is actually the same algorithm that Spotify uses as nearest neighbors for searching what songs you might be interested in. But instead of nearest neighbors, Patrick actually looked at the furthest apart neighbors. So if you're not near a grouping of those nearest neighbors, you might be an anomaly because for some reason in this feature space, you are separate from everyone else. Potentially interesting. And so we can see on the right that LACE actually tags exotic transients even days to weeks earlier than humans searching by eye. So this is supernova 2022 HNT. It's a type 2b supernova. And so you can see we chose to follow this up at that orange dashed line right around peak. But if we had been using LACE at the time, it would have actually recommended that we observe the object 10 days earlier. And so this is just an example of something where the machine is going to be able to parse these objects way faster than any human is going to be able to, and have potentially even deeper insights. You can also see this, if we got this earlier, our spectroscopic follow-up might have more information about the progenitor system, things like that. So really important to be getting these requests as early as possible, only really able to do, especially in the era of big data with machine learning algorithm. Additionally, LACE right now is sending Slack alerts in real time. So this is something to consider. It's taking its recommendations and is connected to the Young Supernova Experiment Slack, and the Slack alerts pop up in a channel, and people are able to come in and kind of thumbs up or thumbs down if they think this is anomalous or not, and decide whether or not they want to follow up. So now we have our pluggable science case, and Haley and Drew did a really amazing job of making this really easy and approachable for someone to come with their science case and just plug in. So all you need to do is create your own feature extraction method. So like I said, for us, it was original, for the 1As, it was originally the Bazin fit, and then moved into that light curve fitting method from Kostya. So you just create your own feature extraction method. You create your own classifier for your science case. So like I said, for the 1As, it was this random forest 1A classifier. And for LACE, it's this random forest plus nearest neighbors. So whatever you need, you just bring it here. And then it's just pluggable. You just deploy your methods as a package, and then importing them into the virtual environment. And once that's all done, it's really as easy as, importing everything that you need, and then just LACE RESSPECT classifier dot the LACE feature extractor, and then so just importing these objects, and then it's pretty much good to go. something that we didn't quite get to, but I'm still interested in doing in the future, is creating kind of a web service for the LSST Spectroscopic Recommendation System. So this would look like a drop-down menu of all of these modules and with an other category, so you can upload your own module. It would do things like pull up all the recommended objects. You would be able to, click on one so that you can look at the light curve, analyze it more, investigate, why maybe it was recommended by your recommendation system, keeps that human in the loop to make sure we're still spending our spectroscopic time wisely. You can just, select that, have it added to the queue of things you want to follow up that night. And then once you look through all the objects you're interested in, just sending those requests to a Tom or, an Aeon queue, whatever you need for your specific follow-up purposes. So our overall experience of the LINCC Incubator was fantastic. We achieved all of our main goals that we wanted to. We had 2 in-person weeks in Seattle where there was a lot of really great collaboration, some really good conversations, and really figuring out how to make RESSPECT the best it can be. And it was really, really amazing to work with the software engineers. I really liked this quote from Michael right at the end of the incubator where he said that, our code was spaghetti to begin with, and that, they didn't make it not spaghetti, but they separated the spaghetti into separate piles. So I thought that was funny. And I think he was being humble. We really appreciated the work that the software engineers and making this project a success. So future, what has been happening since the LINCC Incubator? And what do we plan going forward? So we've been thinking about creating this new module. So this is Oracle, a new classifier from Ved Shah. It's a hierarchical classification. So this means that instead of just classifying things as, type 1A, type 1B, kilonova all at once, it goes in a hierarchy. It starts at the top with figuring out things are transient or periodic, so separating out, periodic stars and like AGN and things like that from the supernovae and kilonova and that stuff. And then below that, it kind of looks into, short or long duration objects, and then more fine-grainedly does that final classification. So you can almost see this in this GIF I have up here. This is how the confusion matrix evolves as more of the light curve is revealed. And you can see sort of that hierarchy revealing itself where there's clusters of objects. So we see it does a really good job right at the beginning saying things are, yes, definitely a supernova, but maybe uncertain about what type of supernova. And then as time goes on, getting a better fine-grained classification. So this is really state of the art right now, some of the best classification of elastic that we've seen, and is going to be really important for photometric follow-up, especially being able to separate those like, supernova from everything else. Also, I want to note this performs really well with even just 10% of the light curve. Part of this is because it also includes host galaxy information, which we know, depending on the host galaxy, we can learn more about the supernovae within them. It also uses non-detection, so we get a little information about what the supernova was maybe sort of looking like before we actually saw our first real detection. I see a couple things in the chat. Are there any questions?
No, it was a public targeted message for Jeno about the dashboard system when you were showing that slide, Amanda.
Oh, fantastic. Okay. So now that we have Oracle, we're also looking to make that into a anomaly detection algorithm. So we define anomalies here. I think there's like 8 different types of objects, but things like kilonova, parent stability supernova, calcium-rich transients, TDEs, things like that. So my undergrad that I work with, Arjun, is sorting these, is combining the predictions from Oracle and saying whether something is of a class that is those anomalies or not those anomalies. So this is a 70% confidence interval, and you can see it evolving over time in the confusion matrix. So it does a really good job of confidently predicting whether or not something is an anomaly. And we have that 70% confidence threshold and could even go higher because we want to make sure we have a really, really pure set of anomalies. We don't want to be, following up on something boring just because there's like contamination from that. And so what this looks like as the light curve evolves, we can see over here the anomaly score and what that looks like as the light curve progresses, how it does a better job going forward. And we can see, the most likely class as it evolves over time. So yeah, you can see here it's getting better, getting more data points. And honestly, it was a bit tough to find something it didn't do really well on. A lot of the time, even just with the first data point, it is doing a fantastic job of classifying these objects. So just a couple potential modules that we are looking into, if someone has interest in doing, these are just some examples of new modules we'd like to create. Things like looking for kilonova, doing micro lensing or lensing in general, tidal disruption events, changing look AGN, and I think most importantly, your science case. We want to know what you are interested in. We want to work with you, make sure that you're able to plug it in, and make sure everything goes smoothly. And I would be remiss if I didn't say that we're really excited for LSST to start this year. We've been talking about simulated data this whole time, but we've also been working on what spectroscopic follow-up is going to look like once LSST comes online. So we've been working with, like I've said, Foremost and Tides. There's a lot of overlap there, and hopefully getting spectra with them. We've also submitted a few Gemini and SOAR proposals. And so, yeah, hopefully we'll have lots of spectroscopic follow-up time to analyze all these interesting objects that we're going to find with RESSPECT. So finally, just a little summary. We're going to have this much needed recommendation system ready for LSST First Light. And we have expanded RESSPECT science case to include any number of modules that the community has interested in, anything that folks want, we're happy to work with. And future plans for RESSPECT is, now that we've had this little detour of adding this modular metric, I'm getting back to the cosmology analysis, and we'll be reporting on my results very soon. We're looking forward to adding some of these more modules, some of the examples that I showed you, and whatever else folks are interested in. And then just First Light, looking forward to getting alerts within the year, and yeah, really looking forward to applying RESSPECT to real data. Happy to take any questions.
Okay, thanks, Amanda. Do we have questions? I can ask one to get started. So I have a very specific one on one of the spectra you show. So I see there are some difference between the noisy spectra, maybe the slide before that. Yeah, like on the bluer end, like the spectra doesn't quite match, like there's an offset. Is that something simulated, like a calibration effect, or how did this happen?
I think this has to do with the detector and how well it does at observing the bluer wavelengths versus the redder wavelengths.
Okay, thank you. Have more questions?
It's not a question, but I guess I can also add about the kilonova module that Amanda mentioned right at the end. So the SIMA group that I'm the PI of is working with Rubin to implement Rubin TO alerts. So get an LVK alert with a sky map that meets certain criteria. We send that to Rubin along with some tiling so that they can point at it. This would be the other end of it. Once Rubin finds something and says, here's the position of a kilonova, we would want to bump that up in priority and essentially tell every available spectrograph on the planet that they should go point at this thing. So that really is this same group basically putting data into the Rubin system, taking something out of the Rubin system and trying to coordinate it with other facilities. And I think this is hyper exciting. It's interesting for kilonova, but it doesn't have to stop there. If folks want to do similar sorts of things for solar system cases, because found something that's potentially hazardous or whatever, or other science cases, I think we'd be very happy to chat.
Yeah, and kind of based on that also, for feature extractors, your features don't have to be necessarily light curve based. If you're interested in including things like LIGO data or neutrinos, that's definitely something that's possible with RESSPECT.
Colin?
Hey man, great talk. Just really simple question. Can you explain, you mentioned Docker. Could you explain to folks what containers are and how do they help here, or why did you need to use Docker?
Yeah, so Dockers are basically containers that somewhat simulate an entire computer within your computer. So it will instantiate the right version of Python, all the right versions of all the packages, and basically just makes it really easy to spin up something and have it working right away without having to worry about, version control of packages. If things work on a Mac for some reason, but not Windows. This kind of negates all of that. And then this is also something that we tend to do on NERSC. It's just a good way to have modules that communicate with each other and kind of spin up their own instantiation, and that can run kind of separate from the rest of the machine.
Perfect, thanks.
And for a group like the Transient and Variable Science collaboration, those folks can take this Docker container, and if they don't have a resource like NERSC, they can apply for and use NSF Access, which is essentially NSF's free computing service, and simply just run the Docker container in NSF's cloud on, say, Jetstream 2 at Indiana or something like that. And that's how Simmer does a lot of its work now.
Thanks,
Yeah.
Scott.
Hi, Amanda. Thanks for the talk. Do you have any plans to integrate the system with any of the sort of telescope status services? So whether either Rubin, in case it's going to get more data points on your light curve, or the follow-up facility telescope statuses, stati?
I'm not totally sure I follow the question. So like using other telescopes, not just LSST?
In terms of closing the loop and submitting things for sort of follow-up, if you can make the system reactive in terms of what Rubin's going to observe this field, so wait for more data, or Gemini is down and therefore send the spectra someplace else.
Yeah, so we do have, if I can go back here, we do incorporate, telescope resources into this. So if Gemini was down, we might, be able to say like, oh, there's 0 hours of Gemini tonight, so don't recommend objects that would need to be observed by Gemini. We don't currently have something that says, we are going to see this again tomorrow. Wait until we see that second data, or that next data point, before we decide whether to follow up. That would be definitely something really interesting to incorporate. And we'd have considered, though, not just allowing for spectroscopic follow-up, but to say this would be good to follow up photometrically. Like, we don't just want to classify with spectroscopy, but a denser light curve would also help our classification. So recommending, say, like I said, I'm in the young supernova experiment. So if we want to follow up with DECCAM and get more photometry, that's definitely something that we could do.
Tim, actually, maybe I can chime in here a little bit. So Amanda's a fourth year; she needs to graduate, and so once this project is wrapped up, I think RESSPECT is going to be inherited by other folks in DESC and pushed further. The sort of telescope status system that you're talking about is this thing called Heroic for ground-based facilities that LCO is part of through Rachel Street. So this is this hop-enabled real-time observatory information and coordination system, which is having another telecon on my iPad at the same time with Curtis chairing that. Yes, I admit to double zooming. And the point of Heroic is to collect telemetry from telescopes. Where are they pointing? Where are they going to point? And the initial plan is doing this, of course, with DECCAM and the LCO facility, since you already have this. And ultimately, eventually include things like NASA facilities. That's, I'd say, a couple of years out before that system is sufficiently mature enough to integrate into this. It does enable more complicated follow-up patterns than just trigger a single spectrum. And I think the thing that's still missing is automated services that will reduce the data in real time and actually give you an update. So you might want to coordinate multiple facilities. Um, but we also have, or Curtis also has a plan for that.
Okay, I have one more question. So can you say a little more about the strategy? Are you running this nightly and like sending out, I mean, sending recommendations, and are you expecting people to feedback with their classification overnight? Or, I mean, I think this not really very realistic. It's likely like you'll be like getting a spectra in a few days also. So how do you take into account this delay, and how does the strategy works?
Yeah, this is definitely, an ideal simulated scenario. With Gemini and SOAR and those like individual follow-up methods, I don't think we have a way to enforce how fast follow-up happens. With Foremost, I believe there's an agreement that they're going to return. I don't think we get spectra, but we'll get labels within, I want to say 48 hours, 24 or 48 hours, something like that. So we're hopeful there that that could be a somewhat speedy process, but you're definitely right that this could take a bit longer. Also, depending on what algorithm you want your plugin to be, could change the cost of training. If it's really expensive to train, you might not want to train every night, in which case you consider doing something like a monthly training might be worthwhile.
So does that mean if, say, we have Foremost to give us some label every 2 days, that means we will just run this every 2 days once we have some labels to feedback so that we have more information, right?
I mean, they'll be observing, nightly or whenever they can. It's just that those labels will come 2 days after the original observation.
Yeah, I mean, you still run it nightly. You just happen to get labels from 2 nights ago. It's not the end of the world. It's just that the pool set is going to change on different time scales. And when you're appending from the pool set to the training set and doing the actual inner loop that Amanda doesn't have up to retrain, that information is getting updated on different time scales based on how quickly people report to TNS or whatever.
Last call for questions before we wrap up.
But I will point out that's actually the motivation of that part of the response I gave to Tim, that you actually want a automated reduction system for telescopes, and neural networks are getting to the point where they can effectively extract 2D spectra or extract a 1D spectrum from a 2D image, and I think you'll see those projects mature to the point where that's not infeasible in the next few years. So I don't think we have to rely on grad students remaining awake after they've taken the data to reduce the data in the near future. I think this is going to change.
Colin.
Yeah, this is more of just a logistic question, but folks often ask before submitting an incubator proposal how important it was to come in person. Can you just comment briefly on how it was coming in person and why you chose to do that for future generations?
Yeah, I think it was really important to come in person. It let everyone be like, okay, this is our 2 1-week periods where we set aside everything else and we're just going to sit and work with each other. I think it really helped us do a much quicker bouncing ideas off of each other. Yeah, and I think we got pretty much the whole group there all at once, and we were able to work in parallel, make sure that something that I was working on was going to be benefiting Drew, or vice versa. So yeah, I think we got, I don't know about the bulk of the work done in those 2 1-week periods, but definitely they were pivotal in getting the project as complete as it was.
Awesome. That's great feedback to hear. Thank you.
Yeah.
Gautam has a comment.
I mean, this is just also our experience in DESC that we always have these in-person sprint weeks, which are essentially people working together in person, and so much more gets done in them than when you have, distractions like multiple 1 hour Zoom calls each day.
Okay, if there's no more questions, let's thank Amanda again for her fascinating talk. And thanks to everyone for attending the Tech Talk today. Our next Tech Talk will be June the 12th. We'll be joined by Lovro Palavarsa, who will talk about another LINCC Incubator program called PhotoD about stellar photometric distance. In the interim, please join the LSTDA LINCC Tech Talk channel on Slack and the link at list.lsst.org mailing list for more information and future announcement. There's more information, including links to the Rubin community forum and a calendar at our LSTDA website. LINCC Frameworks is also holding a office hour every Thursday at 10 a.m. Pacific, same time as this Tech Talk when this Tech Talk is not happening. If you have an idea for a Tech Talk, we'd love to hear from you. Please feel free to reach out to Colin and I via Slack, email. With permission, today's Tech Talk will be available on our YouTube channel within the next few days. And I hope you have a great rest of your day. Thank you.
Thanks, Mi. I appreciate you hosting.
Thank you.